Hello, this video introduces the ideas of concepts of work and energy, and I'm going to use some weights and gravity to explain this, and I'm over the videos going to connect this up to Newton's laws and create a whole new set of additional rules. So what happens then? Well, I want to pick up this 10 kilogram weight and I'm going to move it 1 meter up, in the air. Do I have to put in effort? Yes, I do, because gravity's pulling it down, isn't it? So I need to have a force here. I need to create a force to lift it up. And therefore, I'm going to have to put in the effort to do that with my body. Let's have a think about what's going on here. That effort, we're going to call work. And what we need to do is start turning that into some maths. So if I can move this up 1 meter, couldn't I? The 10 kilograms, yeah? That would take me some effort. If I moved it up another meter, I'd have to use more effort. I'd have to use double the effort to get it up. And that's telling us the first thing, that if I've got something I have to put a lot of effort into, I have to pull something, well, the more distance I have to move it, the more effort, the more work I'm going to have to do. And of course, against gravity, I'm only interested in lifting it vertically, aren't I? If I actually moved it sideways, I wouldn't be fighting gravity, so it wouldn't take me any effort, and I wouldn't do any work. But the first idea is, my force is going, that I'm battling, going down, then moving it up, it's going to take me effort, isn't it? Second thing is, if I had a 20 kilogram weight or a 30 kilogram weight, it would take more effort, wouldn't it? Because the force that I've got here, the mg, would increase, wouldn't it? So the heavier it is, the greater the force, then that would take more effort. So if we just have a think about that and we define this new term, well, work is going to be force times distance, and those two are in the same direction. So in very broad terms, work is effort by an external force to move an object a distance, yeah? And if that force is varying over the distance, we're going to have to integrate it. And the final bit is what units we're working in. Well, force is in newtons, distance is in meters, so we've got Newton meters. But this is used so often that that's actually been given its own name in the SI system and called joules. And it's not only about work done, it's also going to be, it's all about energy as well. And even if you burn something, you create energy. If you move something, you create energy. So Newton meters are called joules. Let's have a couple of quick examples then where we work through this. First one is, let's say I've got a 10 kilogram weight and I'm going to move it horizontally. And because of friction on the floor, I may have to apply a force of 20 newtons to move it, and I move it 3 meters. So the work I'm going to have to do is the force is 20 newtons, the distance is 3 meters, so I've had to put in an effort of 60 joules. Give you a more advanced example. What happens if the force is varying while we're going along? Well, let's have a use of the Universal Gravitational Law. There it is, that's what it looks like. Force between two bodies is a function of the mass of the two bodies multiplied together, divided by the distance apart squared. We should call that r for the radius, because it's like two bodies circling around each other, and then we've got the gravitational constant, yeah? So it's negative because it's pulling down, isn't it, towards the Earth. So if I've got a satellite up here, here's my satellite, and it's at height radius between the centre of the satellite, centre of mass of the satellite, centre of mass of the Earth. That distance here is going to be r1. Yeah. Then that's what our force setup is. Okay, so if I just let that satellite fall out of its orbit, if it just stopped, it would start falling towards the Earth. And let's let it fall down to this lower height where the radius is reduced to r2. So what we're going to do, well, the work done by gravity, gravity's going to pull it down, isn't it? So it's actually doing work. and we're going to integrate the force by the distance. Yeah, that's dx, but in this case we're using dr because the distance between the two. So subbing that value in, we've got to integrate that function there, and 1 over r squared integrates to minus 1 over r, and our limits are r1 and r2, where it started from, where it went to. This is a square bracket for integration, so there's our integral. And once we've finished that, just sub the values into the bracket, we get our GMM as constant out the front, and we've got 1 over r2 minus 1 over r1. And if r2 is smaller than r1, then 1 over r2 is greater than 1 over r1, so therefore this bracket is positive and the work done is positive. Yeah, that makes sense, doesn't it? Because the gravity is actually going to pull our body down. It will naturally pull it down, so it's doing positive work on it, and that will speed up our satellite, wouldn't it? As it falls, it accelerates, and that's the thing we call kinetic energy, isn't it? Because that work, all that gravitational work there is going to be turned into energy, kinetic energy. So let's go back now, and we'll talk about potential energy. So here's our body, here's our 10 kilograms again. It's lying on the ground. I lift it up and I put it onto a shelf 2 meters up. Yeah, there it is. So I've effectively stored the work done. I put that effort in and I put it up here and I left it there. Yeah, and actually if that weight fell off the shelf, that energy would be released, wouldn't it? And it would turn into kinetic energy. I could use that, a bit like hydroelectric power, isn't it? We got water high and we get it to come down, so it would speed up. So that's called potential energy because effectively we've stored it for future use. So what is that energy going to be? Well, that energy is going to be the work done, force times distance. So that's what we've done. We've stored that energy. Work done, force times distance, well, that's our mg, 10 kilograms times 9.81 times our distance d. So we've actually stored in there 196 joules. That's called potential energy, yeah. And if it fell off the shelf, or if it came off, we could release that and convert it into kinetic energy. We can do a very quick calculation here about what that potential energy is, because it is the work done. So if the work done is the force times the distance, in general terms our force is mg and the distance actually is height, because we don't do any work if we go sideways, do we? It's only, gravity's only doing work going up and down. It has no effect if we don't. So we usually call that height, and therefore we've got a nice equation that the potential energy from gravity, so we call that gravitational potential energy, is actually going to be the mass times the gravitational acceleration times the height. And most people will write that mgh. So there we are. There's our introduction and our first few thoughts on this. Work is the effort of an external force to move an object a distance, yeah? So work equals force times distance, or the integral of force times distance, and it's in joules. Potential energy stores this work ready for use, and the example we've looked at today in the first video is that gravitational potential energy is mgh, mass times gravity times height. So there we go, part 1.